Thank you. Thanks for the intro. It's a pleasure to be back in Berlin and in Protocol Berg. So I'm Andrew. I'm a mathematician, and I work in market design now. And today I'm going to be talking about a design pattern that I've been looking into in decentralized storage and in the storage market. And the aspects of the design pattern are things that I haven't seen talked about that much in the public discourse, and I would like to see more of it. So hopefully we can get some interest started from this. And broadly speaking, it comes under the category of allocation. So in this talk, allocation means a couple of different things. Firstly, in traditional storage systems, you've got the problem of allocating data to physical storage locations. So the question is, when we get a data object going into the system, how do we decide where in the storage backend it's going to go? And how do we keep track of this? In other words, where do we store the allocation table? And in decentralized storage, we face a new problem, which is that we have multiple providers who need to be incentivized, and we have to deal with compensating them for providing their resources. So we have a question of who pays for these resources and how are the payments determined. In the typical case where the uploader is the person who pays, how is the fee rate fixed? And in the interesting case for decentralized storage, where the uploader's data is split across multiple providers, how is the fee split between those providers? How are they each compensated? And that's the question that I'm mainly going to be talking about today. So first, the setup. Suppose I've got a storage customer who's bid X dollars to store some amount of data for a certain time period. Now the customer wants to make use of the key features of decentralized storage, so he's going to expand his data first, introducing some redundancy, either by replication or more generally by erasure coding, and then he's going to chop the data up and split it across several different providers. And there's basically two reasons he wants to do this. One is, perhaps the more basic one, is risk management. Basically, if one of the providers goes down, he can recover his data and reconstruct from the remaining providers. And then there's a kind of an edge computing performance reason where if you have a globally distributed set of entities requesting the data, they can recover the data from the set of storage providers who are closest to them and thereby achieve best performance. So for simplicity, I'm not going to talk about erasure coding. I'm just going to pretend our storage customer is going to fully replicate his data and make K copies of it. And he's going to find K providers, each of which is going to host one copy. So each provider is providing an identical service. Question, how should each of the replica providers be compensated out of the customer's bid? Well, there's a kind of obvious answer you might be thinking of. But before we get to that, we'll go to what I call a non-answer. We don't decide anything as the system designers. We simply allow customers to figure out everything individually with each provider. So this is direct negotiation. The client's going to seek out K separate providers and make K separate deals to store the K copies of the data completely independently. This is basically how Filecoin deals work on the basic layer. It's kind of, in some sense, can be considered efficient, but only by ignoring transaction costs. That's rather a big thing to ignore because discovering the counterparties and negotiating with them is costly and requires domain knowledge. It's non-atomic, and it's highly illiquid. Direct negotiation, direct contracting is super illiquid marketplace. So we're not going to do a cop-out. We're going to actually try to design something for a principled system for allocating these fees. First proper attempt. Each provider provides exactly the same service. They should receive the same payment. So we just divide the payment by K and split it up evenly. There's actually two problems with this approach. I'll talk about the second one later. The first problem that's kind of obvious to anyone who thinks about blockchains is that it's vulnerable to Sybil attacks. That is, how does the customer know that he's dealing with K separate providers who are producing K separate replicas and not just one provider with K different hats, storing only one replica and serving it through K different gateways? Of course, if it's the second thing, it completely defeats the purpose of having K replicas. It defeats the risk management and the performance purpose because everything's just in the same place and a fault will affect all K replicas equally, all K fake replicas. So we need a Sybil resistance mechanism. And again, because we all think about blockchains. We probably know a couple of Sybil resistance mechanisms. The general way that one does this is you introduce, you make it costly to generate an identity. So you introduce a resource that can be committed that needs to be committed in order to provide the service, in order to have an identity. Classical examples are work and stake. Then each provider is going to provide some proportion of the total resource that was committed, and then they're compensated in kind for that resource. Now, you can't just use any old resource for this. It needs to be something that is able to be registered on chain where the payments are being figured out. The chain needs to be able to know that that resource was committed. And not all resources can be proved in this way, and some are easier to prove than others. So that's why you see in typical cases proof of work, for which cryptographic constructions have been known for a long time. And then you've got things which is just by intrinsically registered on chain already, like stake balances. Now, given that a service for request for real resources has happened, you might think that the most natural resource that should be committed for Sybil resistance is the resource that was demanded. In this case, it's storage for one replica, an amount of storage equal to what was demanded. That is currently storing the replica. Unfortunately, this is kind of hard to produce a cryptographic proof for. There are ways to do it, and that is how Filecoin works. But the solution is very complex, it's very compute heavy, and judging by the limited deployment of this solution, it's obviously not currently that practical at all scales. So we would like a way to sidestep this requirement. Side benefit of this is if we can sidestep the proof requirement, we can also apply it to other situations where we don't know sensible cryptographic constructions. So we want a kind of a pure market mechanism for deciding these payments. Given that we're not going to use a resource, we're not going to prove a resource that's related to the actual service, we're going to use a completely different resource. Isn't that just a crazy hack? Shouldn't we just try harder to come up with a good practical proof of replication? We probably should work harder to come up with better proofs, but I would argue that it's actually not a crazy hack. It's actually completely normal. And in fact, you would have to do it anyway, even if you did manage to prove the resource that's being solved. And the reason is to do with the way that storage providers are allocated to jobs. If the waiting resource for Sybil resistance is the same as the one being sold, that is storage for one replica, then the total amount corresponding to this deal is fixed by the amount demanded. And then, in this case, it's fixed and it's divided up into equal shares because each person provides one replica. On the other hand, in a healthy market, there's more of the waiting resource available than is being demanded. So then you have the question of, you have a fixed price deal available to be consumed by some storage providers. How do you decide which of the many storage providers in the market get to settle the deal at that fixed price? You need a secondary allocation mechanism. And I claim that that secondary allocation mechanism, this is a kind of a pseudo-proof, necessarily introduces competition on some factor other than the actual service being provided because that's fixed. So we have to do it anyway. What are some examples of these things? Well, in what you might call a standard competitive market environment, the way that providers are allocated, or the primary way in which providers who are basically fungible are allocated to tasks is basically on price competition. So the customer is just going to find the people with the lowest price, assuming the products are all identical. Flipping the perspective on this a bit, the resource being committed by storage providers in this is money. The storage providers bid on how much revenue they're prepared to forego in order to get into that allocation. And the reason that this works for selecting storage providers has nothing to do with the fact that the money is saved by the customer. That's incidental. The important thing is the storage providers pay it somewhere. So it also means that it doesn't have to be normal price competition. There could be the same dimension of competition could be introduced in the form of a participation fee that storage providers pay into the service. This participation fee could be given as a rebate to customers. It could be redistributed, or it could be deployed as the system designers see fit. It's nothing to do with the it has the same sort of allocative effect and the same incentive pressures on storage providers. And a second kind of typical way to do this is on a first-come, first-served basis. So basically, once the customer's bid is out in the air, the first K storage providers who come and respond to the bid are going to be allocated. And in this case, the resources, the extra resources the storage providers have to commit, whatever resources are needed to get their responses acknowledged in the correct, high enough in the order to be able to settle the deal. So for example, if this auction is being carried out on chain, the resources you need to commit are those needed to get your transaction high up in the block, which if you're familiar with the situation in MEV wars, is basically kind of unrelated to any skills involved in providing a storage service, apart from general DevOps infra ability. And a disadvantage that it has compared to the price competition situation is that the extra value that these guys are paying to get into the queue is going to the sequencer, instead of going back into the system, which is what happens in price competition, which is a shame because it's not that hard to make it go back into the system. To use a sort of modern buzzword for this, the problem is the system does not capture its own MEV. Okay, so we've talked about, I've argued that the commitment of arbitrary resources that have nothing to do with storage is actually a good and normal way to distribute rewards among storage providers. Before I go into our case study, I'm going to introduce one more perspective shift, which is to do with the multiplicity or the number of entities involved in deals. So when I introduced the setting, I treated it as though we have a single storage client which is going to try to achieve a direct contract with some storage providers to upload some data. But that's not how it needs to work, and it's not even a particularly good way for it to work in some sense. It's not how modern multi-tenant storage systems work. Instead, what we would like to do is be able to multiplex between both the storage provider side and the storage client side at once. Here's how this can work. All of the storage providers aggregate their storage into a single pool, creating a highly liquid supply of storage. And then multiple storage customers can come and interact with the pool without making direct contracts with storage providers. So instead of doing that, you go and you try to get a quota representing a claim over a part of the storage capacity of the pool for a certain amount of time. This claim doesn't have to correspond to a particular data set. It doesn't correspond to a specific set of storage providers or backing hardware. And then similarly, the payments have to go into a pool, and this pool is redistributed to all storage providers. This is how many traditional multi-user storage systems work. Not so many, haven't seen very much of it in decentralized storage, but I expect to see more of it because it's very nice for the user perspective, basically. And one might ask, okay, we've introduced some complication here by adding more multiplexing on the client side. Does this massively complicate the problem of redistributing revenue? No, it does not. It's basically the same exact problem, except the X dollars needs to be interpreted instead of the bid of a single client to be the aggregated network revenue pot that's being paid out and redistributed to storage providers. And the same solutions basically have the same effects. Now, I'm going to talk about EthSwarm Protocol. So some research into EthSwarm Protocol and its incentive system was what stimulated the abstractions I talked about in the first 3/4 of the talk. So I'm going to talk about this in the context of the language I've introduced. Just to disclaim, the version of Swarm Protocol that I'm going to talk about is a slightly idealized form with many simplifications. In spirit, the sort of core is the same, I think. So in the EthSwarm Protocol, storage providers all pool, many thousands of them, their storage into a big aggregated set. Uploaders do not communicate with storage providers directly. Instead, they purchase storage quotas, claims over that pool from a smart contract. And the amount that money that they pay is determined by some on-chain price controller mechanism, the details of which I will sweep under the rug. Their fees all go into a pot, which accumulates each epoch and then gets paid out and redistributed among all service providers. Importantly, there's nothing linking the specific fee of a storage client's upload with the storage providers that will store that guy's data. It's all just accumulated and then redistributed to the program as a whole, to the project as a whole. How is this distribution achieved? Storage providers deposit tokens into a registry contract, so it's going to be a stake-weighted distribution. Each round, the address space is split up into segments. A segment is selected randomly, and then within that segment, storage providers are paid proportionally to their stake within that range. So this token, which is the network token, is used as the Sybil resistance weighting resource. So what effects do we get from this? Well, one nice feature of using a proof of stake as opposed to a proof of work market to weight these things is that if the market for tokens is liquid enough, the SPs don't need to compete substantially on the cost of getting each token. This is in contrast to the case where Bitcoin miners, major facet of competition there is obtaining cheap access to energy. So which in this case would again be perhaps not the most important thing for the competition, for the provision of the service. So if we assume this idealized form where storage providers don't have to get different prices for the token depending on which market they're in, the two major remaining dimensions for competition are the costs of managing the stake positions, which I will sweep under the rug, and the cost of running the actual storage service. And so a result that you can prove under these conditions is that under sufficient free trade conditions, where sufficient free trade means that stake positions can be moved around and transferred in sufficiently many ways to allow trades to occur between different stakers, then the invisible hand of markets will move the stake to the storage providers with the lowest cost on these factors, which if as we are ignoring the sort of token price differences and cost of management for the stake positions, flows eventually to the storage service. So this incentivizes storage providers to invest in reducing costs of running the actual service that the network provides. And ultimately, again, you need to make a bunch of assumptions here, which I won't have time to go into, will allow the price controller mechanism to settle down and communicate those investments to price savings for customers. So the take home here, and again, if you remember nothing else from this talk, please remember this. Perhaps surprising at first, the fact that we've required the commitment, storage providers to commit an unrelated resource in some kind of weighting competition has stimulated competition on the factors we actually care about, which is the cost of providing a storage service. Okay, that's basically it. I'm a little bit early. Take homes are, let's talk more about allocation mechanisms. I don't see as much conversation about it as I would enjoy seeing, so come and talk to me about it if you're interested. If, as a modern, like a user-friendly storage system should, the system itself decides about where the objects are going to go, it also needs to decide about where the revenue is going to go and how the storage providers are compensated. And then, again, to reiterate the main point, mechanisms that stimulate competition on dimensions that are relevant to the service can lead to improved service quality. So yeah, please come after me after the talk, especially if you're building or running infrastructure for a decentralized storage system. Talk to me after the talk or reach me out on TG. That's all.
All right, thank you so much, Andrew. That was great. So moving into Q&A, you still have the QR code up there, and we already have 2 questions. So question number 1, nothing got upvoted yet, so please, yeah, if you have more questions, you can prioritize as well. So first question, how does this incentivize availability for retrieval?
Yeah, so the availability for retrieval is kind of a separate thing that's just not part of the mechanism I discussed. You just layer on top of that a normal like data availability type construction with a storage proof. I guess I probably should have mentioned it, but the point was that the data availability proof doesn't prove how much of the resource was committed, doesn't prove how much storage was used, which is important for risk management. So assuming you've got some kind of basic data availability construction, you can layer it with this to achieve something.
Makes sense. So next question is, aren't the lowest cost SPs the ones who don't actually hold the data, or those under Sybil?
Are the lowest cost SPs the one who don't? Right. So, yes, that's a good question. I guess in a system where you don't have, I guess like the points I was going to make are not providing a complete storage proof system, but more arguing that something that has to be layered with other systems. So yeah, I guess what I presented now in the example doesn't really block Sybil resistance, doesn't really block this type of behavior, but it substantially removes the obvious incentives for doing so. But yeah, like I don't have a super strong answer to that right now, so we should discuss it.
Good points made. So last question, or one more question at least. What's the biggest risk to the future viability of self-sustaining storage systems?
Oh, that's a big question.
We have 6 more minutes, so
I might have to think about that one.
Extend your talk.
Yeah, I guess I don't know if I can think about like the future, like all future. Like it's kind of a long road ahead for a lot of these things. In the immediate future, I see like a kind of UX and transparency issues. In principle, like it can be, it's hard. There's a lot of fragmentation, and some sense this was talked about in the previous talk between different storage ecosystems, and there's little common language and ways of evaluating things. So it's hard for people to understand how to consume storage. It's hard for people to understand what guarantees are offered, and it's hard to understand how to actually get in there and buy the storage. And then, yeah, like again, going back to transparency, like monitoring risks and monitoring the repair rates and health of networks. Those are sort of the immediate things that I see. But there's like a longer future ahead of that I didn't get to yet.
Much things to discuss in future talks at Protocol Berg V3.